Good afternoon, everyone. I am Chanda Devnath. I am pursuing my PhD from ISER Berhampur. So I am the TA of this course, Mechanism in Organic Chemistry, instructed by Professor Nandita Madhavan. So in the previous class, we were discussing about some concept of different type of organic mechanism. So here is the continuation. Before that, I will give a recap where that in previous class we discussed about SN2 reaction and its energy diagram. After that, we discussed about some concept of elimination, followed by the difference between substitution and elimination. Like if one substrate is given to you and same type of reagent is given, how will you determine that the substrate will undergo substitution or elimination? So we discussed about that also. Then I gave some problem. So among these four, two of them we solved in the last class, and two of them I told you to try by yours. So let's try to solve these two. These two answers of these two questions has been solved in last classes. If you are unable to get the answer, whoever is joining for the first time in this class, you can go and check the last class video, then where I have discussed about these two problems, which is based on simple substitution, different type of. So let's solve these two. I hope you guys have tried these two also and got your answer, but just to check, and for others who haven't got it correctly, or just for a recheck that it is correct or not, we try to solve it together. So what will happen? First, there is a leaving group, bromine, so it will get eliminated first, and that will give us this carbocation. Now what is the hybridization of this carbocation? This is 2 degree. This is 2 degree, and we know from the concept of SN1 and E1, if the carbocation is 1 degree or 2 degree and the substrate has a probability or opportunity to enhance the hybridization to 3 degree, then it will go through that. So here is a chance if it shifts one of the methyl group from here. Now it can shift, there is 3 groups, 2 methyl and 1 ethyl. There is 2 carbon, so 2 methyl, this carbon, and always the shifting will be happen from the adjacent carbon. Now this adjacent carbon to this carbocation carbon, this adjacent carbon has 3 groups. One is this ethyl group and 2 methyl group. Now we all know to shift a small part or small box is easier to shift a big box. If you have to shift from one place to another, a big box and a small box, you can easily shift a small box. So obviously when the shifting of this methyl is easier than shifting of this ethyl group, that's why one of the methyl will be shifted to this carbon. So methyl one to shift. Okay, so what do we get? after this shifting, then this methyl group has been shifted to this position. So there will be a one bond less, so the carbocation will be shifted to this position. So what is the hybridization of this carbocation now? So this is 3 degree. 3 degree carbocation are stable. So that's why this carbocation will take part in further reaction, where now methanol is given. So this methanol can act as a nucleophile also. So this oxygen lone pair will attack to this position and we will get oxygen will plus as it given on of its lone pair, so it will be like this. Now as oxygen is positively charged, so it will remove H plus from the system and we will get this as our desired product. What will happen? It will give minus H plus so we will get this one as our product. Okay. So same case will happen in this one also. This will be removed and we will get this carbocation. There is nothing. It's not anything. We will get this carbocation. So now this carbocation is 2 degree. So there, if there is a chance to shift, now there is one hydrogen atom and one methyl atom. So if we shift this methyl, what will be the hybridization? If we shift the methyl, it will be again 2 degree but benzylic. And if we shift the hydrogen, it will be 3 degree and benzylic. So there's a, if I see if hydrogen shift is happening, then we will get, I am doing the both so that you can get an idea how to choose when methyl will be shifted, because some of the time I am shifting the methyl, some of the time I am shifting the hydrogen. So you have to get an idea that which bond will be shifted. So if we shift the hydrogen, we will get this carbocation. But if we shift the methyl, then we will get sorry, we shifted the hydrogen, right? There will be one I. So we shifted the hydrogen, and here if we shift the methyl, it will be like this. So this is also, this is it. So in this case, this carbocation is 3 degree and benzylic because it is adjacent to the phenyl ring, and in this one, this is 2 degree and benzylic. So which one is more stable? We all know that 3 degree is more stable. So this pathway will be more stable. This will not this shifting will not take place. So this one will be our intermediate, and similarly instead of here they have given methanol, while here they are given isopropanol. What is isopropanol? O means 3 carbon. Why it is iso? Whenever the 3 carbon are like 1 by 1, it will be normal propanol. If the 3 carbon are like this one, these are called isopropanol. So they are given isopropanol. So this in a similar way like methanol. So I am not drawing that. This OH will attack and we will get this one as our product. Okay. Here in this case, in this reaction, this methanol and this isopropanol is acting as a solvent as well as nucleophile. We don't have to give any other solvent. If you have gone to any laboratory or performed any reaction, we know that to perform a reaction, most of the cases we have to give some solvents to occur. Like if I am making a solution of salt and sugar, it can't be mixed in a solid form. You have to give water to dissolve them and mix with each other, and we will get a mixed taste of salt and sugar. So to perform a reaction, to keep both all the reactant in a same reaction mixture, sometimes we need a solvent. But in this type of reaction, where our reagent and solvent both are same, we don't have to give any, because here methanol and alcohols can act as a solvent also, because it can dissolve this type of organic compound, and this can attack as a nucleophile. Okay, so this will be our answer. Let's move on to our next problem which we are given to solve. This is also the last two was based on SN1. These two are based on SN1, and next question was based on, see here, no nucleophile has entered. No nucleophile has been entered. So this is not substitution. Substitution means by eliminating something, you are entering something, thus substituting something. Then that will be, if there is an incorporation of a new group, that will be a substitution. But if there is no incorporation of any group, that is just a elimination type, that will be elimination. But here actually it's, now here it is also substitution, because here the nucleophile is not a external nucleophile. See here, there is a double bond. There is a double bond in medium. That's why I gave this question. In most of the cases, in case of substitution, we are giving a nucleophile which substitute our leaving group, which usually substitutes our leaving group. But here, then no nucleophile has been entered. So how can you determine that it is substitution or elimination? But here there is a double bond. So in this case, this double bond acts as a nucleophile. This double bond itself acts as a nucleophile. So let's start. Sorry. So what will happen? Like all SN1 reaction, this acid will give H plus, and this okay. So this will remove from the system. Now what will happen? So there is a double bond. So here you can see there is a single ring and there is a double ring. So from that one you can get an idea. There will be ring closing. There will be a ring closing. That somehow this double bond will attack and there will form a ring. So you just count the number of carbon. 1, 2, 3, 4, 5, 6. So if we attack from this center, then it is possible to form a 6-member ring, because here this long chain is giving 4 carbon and these 2 are giving 2. So it can form a 6-member. So the attack will be like this one. Here we have to sometimes, if here the product was not drawn, sometimes you have a confusion that what will form. It will form a 6-member ring, or if there will be hydrogen shifting or not. You will get there will be chances of hydrogen shifting, but as the product is already given, so we will just draw the mechanism according to our product. If the product is not given, if there is a chance of hydrogen shifting and get a higher degree compound, we can do that. But here there will be no shifting, because without shifting we can get a 6-member ring. If shifting occurs from this position to this carbocation center will be shifted to this position and we will get a 5-member ring. 6 fused rings are stable than that of 6-5 fused ring, because we know 6 fused ring will stay as like this type of. So 6 fused rings are stable than that of 6-5 ring. So that's why this type of ring closing will perform and will get so there will be a positive charge as double bond attack and there is a scarcity of electron. And if you count, this is 1, 2, 3, 4, 5, 6. I will just give a number. 1, 2, 3, 4. So here if you give the number, whenever if you get confused how the ring is formed, just give the number to the carbons, then you will get an idea. Okay. Then simple. There is one hydrogen. So this will come. Kind of elimination type of process. And we get our desired product. Okay. I think it was easy and clear. So let's go to our next one. So today's concept which we will discuss, that is the elimination we have discussed last week was E1 and E2. So it was the remaining one, that is E1CV. What is the full form of that? E1, you know that unimolecular elimination, and CV means conjugate base. So what is the difference from its simple E1 and E1CV? In case of E1, what we form? In case of E1, we form a carbocation. Here you can see. In case of E1, we form a carbocation. But in case of E1CV, we form a conjugate base, that is a carboanion. That is the difference. So if you E1 means carbocation, that is positive, and E1CV means carbanion, means negative. Okay. So now, what are the main points of this one? This is the unimolecular reaction and does not involve base, that is in rate determining. We know that the number of components involved in the rate determining step determines the molecularity of the reaction. So the base is not involved in the rate determining step. So what happened in this reaction? First, the carbon ion gets removed by a strong base which is adjacent to the carbonyl group. So to eliminate a hydrogen atom or H plus from a system, that H plus should be enough acidic. That is, after elimination of this H plus, whatever anion will generate, that anion should be somewhat stable. Otherwise, it will be difficult to remove hydrogen from a system. You can't remove hydrogen from any carbon. Then it will hydrogen removal from a heteroatom is easy, because after removal of heteroatom, after removal of the hydrogen, the heteroatom gets a negative charge, and a heteroatom can due to its high electronegativity in itself, it can stabilize that negative charge. But when it is a carbon atom is not a heteroatom or a electronegative atom. So whenever it's a carbon atom, removal of H plus is not that much favorable until after removing the H plus, the carbon ion has that much of stability. So in this case, E1Cb, there is a restriction. In case of E1 or E2, there is no such specific requirement that the lone pair should be, that leaving group should be at that place or hydrogen should be at that place. But in case of E1Cb, that hydrogen which is getting removed should be adjacent to a carbonyl atom or any electron which has that minus R effect, that is minus resonance effect, to stabilize this carbon ion. So this hydrogen atom will be removed and it will generate this carbon ion. It will generate this carbon ion, and this carbon ion has a stability by this carbonyl atom, and we will get this stabilized anionic intermediate. And now through this type of extended conjugation, this leaving group will get removed from the system and will get our expected double bond. So if we look into the energy diagram, this is similar to the SN1 type of reaction where the intermediate forms and this intermediate take part in the second reaction. But the difference from the SN1 reaction is that in case of SN1 reaction, the first step was the rate determining step. As in the first step, the leaving group removed from the system, and in the second step, the nucleophile attacks, or in case of E1 also. So the first step was the rate determining step, and in the first step, this just was the removal of the leaving group which didn't need any nucleophile or something. That's why it was SN1. But in case of this type of E1Cb, the second step is the rate determining step. So first step, when the base is involved, that is not the rate determining step, because it needs less amount of activation energy. But in the second step, when this carbon ion take part in this type of reaction, that step needs higher amount of activation energy. So this is the slowest step and the rate determining step. Rate determining step means this is slower than the first one. Whichever step is the slowest in a multi-step reaction, that will be its rate determining step, because suppose a group of people are walking. Some are walking fast, some are walking slow or something, but they are competing in a team. So now they are walking on a road or any competition or something. The last person who crossed the line, that person will determine the fate of the team. That person will determine the fate of the team, who that team has won or not. That is what happening. Whoever is walking slow, whatever step is the slowest step, that is determining the fate of the reaction, that the reaction is slow or fast. So the slowest step determines the rate of the reaction. Okay. So this is the energy diagram. So I will discuss about the energy diagram today in a elaborate after some slides. Why you can get, why I am saying this, what portion I am saying activation energy and not, that I will discuss after that, so that you will get an idea how I am saying that this amount of activation energy is needed. Okay, so here are some examples. I'll just give 5 seconds. You get an idea that you have to form a carbon ion first, then this carbon ion will remove the leaving group from the system. By this idea, just try to solve these two, then we will solve together. I'll just give 10 seconds. Okay, let's solve. I hope many of you has got the answer. So here, what is the electron withdrawing group? This is the electron withdrawing group. So adjacent this there is a hydrogen. So there is a base. This base will remove. Sorry, before that, if there is a whenever there is a heteroatom, if you are giving a base, from first it will take a proton from at this position. It will not take proton from carbon. If there is a heteroatom and heteroatom has a base, when heteroatom has a hydrogen, whenever you are adding base, it will take proton from the heteroatom first. So it will take proton from this heteroatom first, and it will generate this one. Whenever you are performing reaction in laboratory, you will get an idea that if you are thinking that I am giving base and it's not in your hand, right? If you are giving, you can't control your base, that no, don't go that position, you have to take proton from this position. You can't control your base. So whenever there is a heteroatom, it will take proton from that position. So it will take proton from this position first. So now this O minus, now this methyl chloride is given. So methyl from this methyl, this is the structure of actually methyl chloride. So if methyl chloride is given, so it will attack here. Actually we are just protecting the OH here. We are protecting the OH, or because first it will do this one, or making it a good leaving group also. So it will form this OMS as chloride is removed. So now it is not methyl chloride, is MES, methyl hydroxide. So it will be OMS. Now what I said here, base is the solvent. Here base is the solvent. So whenever the base is the solvent, there is another equivalent of base is remaining, because you are adding base in a excess amount, right? So ET3N is still there. It's not that ET3N is over. ET3N is still there in the medium. Just one molecule of ET3N has been used. So there is another molecule of ET3N. So that will take proton from this position, and that will generate So now this carbon ion, what will happen? This goes here. This will be moved. And we will get this as our product. Okay? Understood? Now this question, the next question is easier, I guess, because everything is same. Just instead of ET3N, they have given pyridine. Pyridine also has a nitrogen, and pyridine can act as a base also. In the first class, when we are discussing about aromaticity, in there I have told that in pyridine nitrogen has a lone pair, and that lone pair not get involved in the ring, because the involved ring itself is aromatic. So it does not need the leaving group of the lone pair to get that aromaticity. So the leaving group of the lone pair is not diffused in the total ring. In the first class, if you can, the slides are given, if you want you can go and check. Here I have shown an electromagnetic field diagram or something, where they have proved that the nitrogen lone pair is at the on the nitrogen atom only. So it is localized on the nitrogen atom only. It is not diffused in the ring. So the pyridine nitrogen lone pair is highly basic to trap a proton, because the lone pair is not diffused in the ring. You can go and check. So this pyridine can act as this type of ET3N and remove one proton. So here what is the leaving? This is the leaving group, and adjacent to this there is a hydrogen, and this hydrogen gets stabilized by this carbonyl atom. So this hydrogen gets removed, and the product will be this one. If anyone has doubt about the mechanism, Just try by yourself following this above one. I think you will get your answer correctly. I am not doing the mechanism again because it's same. Okay. I think it's clear. Let's go to our next question. This one. So they have given different type of reagent and they have already said that it will be go through a E1 CV. It will go through E1 CV and you have to form this product. So just try. I just give 5 seconds. Just think. So let's try. So what will happen? So they are given H plus and H2O. So first there is a ester group and you can see that there is a cyclization by this oxygen. So there is a formation of a lactam. Whenever there is a ester, ring ester, in a cyclized ring there is a ester that is called lactam. Ester in a ring system is called lactam. So there is a formation of lactam. So obviously this oxygen has attacked here and removed this one. Then we will get, just if you count the carbon, the number of atom 1, 2, 3, 4, 5. So this center will attack here, then we will get this 5-member ring. So what will happen? So first this oxygen attack formation of this one. Now increase of base, this base will take a proton from this position like this and we will get a carbon ion. Undergoes this type of etoenol tautomerism and give this type of stabilized intermediate, and that will again come here and remove our leaving group from the system, and this will be our desired product. Okay, I hope UNCB is now clear. If somehow is, whenever there is a bad leaving group, here I have already discussed, whenever there is a poor leaving group like hydroxide, in that case mainly the E1CP get involved, because in case of good nucleophile, E1 and E2 can take place, but when there is a bad nucleophile, to remove that bad leaving group, when there is a bad leaving group, to remove that leaving group, you need a high charge of nucleophile. Only a nucleophile can't remove that one. So, or a normal hydride can't remove that leaving group. That's why in that case we generate a negative center, and that negative center has a huge electron density to remove that leaving group from the system. Okay. So let's go to our next topic, that is electrophilic aromatic substitution. It was remaining in that list we shared different type of substitution and elimination. It was the remaining one which we haven't discussed. So after this one we have all discussed all type of substitution and elimination. We have discussed all after this one it will be, we have all discussed. If you anyone has interest to know the other one, you can follow you can get and check the other two videos. So we have, by this one we will finish the substitution and elimination. So after that we will move into the theoretical concept of a reaction mechanism, where different type of principle we will discuss, like Hammond principle and all. That we will discuss in the next upcoming classes. If you have any doubt, because ma'am is already teaching all those topics, so if any portion should be you need some extra questions to solve, you can ask me, then I will try to arrange some questions on that specific topic for you. So if you have any doubt, you can try to contact me. I think the email ID and everything is given, so you can try to go and you can try to contact me by if you need any questions regarding that. So I will go to those topics in the upcoming classes. By this one, then substitution and elimination will be finished. So what is electrophilic aromatic substitution? It is an organic reaction in which an atom that is attached to an aromatic system is replaced by an electrophile. From the name you can idea that the last SN1, SN2 are SN1. So it is substitution nucleophilic, first order and second order, SN1, SN2. But here substitution E, electrophilic aromatic. So it is a aromatics for aromatic system, and it is a electrophilic substitution. Substitution two types I have discussed. One is nucleophilic, one other is electrophilic. If it is nucleophilic, means nucleophile is coming and substituting something from the substrate. And electrophilic substitution means externally a electrophile is coming and substituting something from the substrate. That is electrophilic. Understood? Suppose you have some leaving group and the electrophile is coming and kicking out from your system. That is called electrophilic substitution. So some of the most important electrophilic substitution examples are aromatic nitration, aromatic halogenation. Nitration means NO2 will come and substitute leaving group from your system. Halogenation means a halogen will come and substitute leaving group from your system. Sulfonation, a sulfate will come and substitute. And last one is alkylation. So that alkyl group means like methyl, ethyl, this type of alkyl group will come and substitute something from your system. So this is the in general mechanism where this electrophile will come and our system will take this electrophile, and by this is the sigma complex where by which this intermediate get stabilization. After that, this hydrogen atom get eliminated and we will get this substituted product. So here this hydrogen, there is a hydrogen. So this hydrogen is getting substituted by this electrophile. Okay. So this hydrogen is getting substituted by this electrophile. So let's try to look into the energy diagram. Why we are checking the energy diagram again and again? Because after that we will talk about energy diagram. So you can correlate how for a reaction, and suppose if you don't know the reaction and somehow you were given the energy diagram only, how to determine that what will be the reaction. So get the idea, I am discussing energy diagram for every reaction. So for your better concept, you can draw notes or something that SN1, then this energy diagram, SN2, this energy. You can make a short note, then it will be a very quick recap for you that if it is SN1, energy diagram will be like this, so that if somehow any reaction is any energy, some in case of net or gate, sometimes they have given the energy diagram and they gave 4 examples of reaction for which reaction this type of energy diagram is possible. Now you know, suppose they have given 4 options. One option is the example of SN2, second option is an example of U1, third option is example of aromatic substitution, and third like this one. And you know this type of energy diagram is possible for SN1 only. So you will just choose the reaction which is SN1. So you can make a short note for that, that can help you. So this is like that. So now what will happen? This is our substrate. So first the electrophile enters, and this need a huge amount of activation energy, and after that this electrophile get some stability through resonance, and through removal of the hydrogen we will get our desired product. Okay. So this is the first step, where here see this is 2-step process. First the electrophile enters, second the hydride elimination. The first step is the slow step, where the electrophile enters. So this is our first step, first, not fast, first. This is our first ever step, and which is the slowest step and our rate determining step. So this is the example where I was talking about different type of halogenation, nitration, sulfonation can be performed through this type of aromatic substitution. So here I have given some examples. I will just give, here I have given the in general mechanism. From that one you can get an idea. So just try to solve. I will just give 1 minute. Then we will solve one by one together. Let's solve. So first one is our bromination. So what will first, this is a Lewis base, Lewis acid. This is a Lewis acid. Iron has a D6 configuration. Iron has D6 configuration, so it has vacant d orbital. So D6 configuration, and here the iron is at +3 state. So that is D5. So it has some vacant d orbital. So it will when you are adding bromine has lone pair. So as it has vacant d orbital, so one of the bromine will attack to this vacant d orbital. It will form that will generate plus. So this is the electrophile. So now whenever there is a NO2 group, that is electron withdrawing group, whenever in case of aromatic substitution, whenever is a electron withdrawing group, that will be a meta orienting. So the upcoming electrophile will enters at the meta position with respect to this controlling group. So whenever there is a electron withdrawing group, it will be a meta orienting. So entering electrophile will enters at the meta position, and whenever it is electron donating like methyl or OH, then it will be orthopara orienting, like the entering electrophile will enter at the ortho or para, depending on the steric hindrance. Ortho-para orienting. I think these things are discussed in first year or some. You guys know or not? I don't know. But this is the thing. So whenever there is an electron withdrawing group, the entering group is meta orienting. If we draw the mechanism, I will try to draw the elaborate mechanism in the next class. I try to if someone has doubt why this type of meta orienting and orthopara orienting is happening, you guys can ask me. Then I will try to, in the next class, I will try to incorporate some slides based on that, because it will need to draw huge structures and different type of structures. So I need a preparation. I haven't included the structures. So I'm just trying. If from this one you can get an idea, then contact me or ask me. I will try to incorporate that in the next class. So if there is a NO2 group, so if you can see this NO2 group, there is a probability of resonance. So if this resonance happens, like this goes here, so there will be a positive charge at this position, and if it goes here, there will be a positive charge at this position. So there is electron scarcity at the ortho and para position, and electrophile is entering. So electrophile always choose a position where there is electron density, because it itself has no electron. So it will try to go at that position where there is some electron density is there. So in case of electron withdrawing group, there is electron scarcity at ortho and para position. That's why comparatively the meta position is electron efficient. So that's why the electrophile chooses that type of meta position. If by this thing you haven't got the idea, I will discuss in the next class. So you can get an idea from this one that in case of electron withdrawing group there is a partial positive charge as ortho and para position. So due to this electron scarcity, the electrophile does not choose this position, it will just choose the meta position. Okay, and in case of electron donating group, suppose there is a OH group, then that will be electron donating group. The electronic movement will be like this way, and it goes here. So there is a partial negative charge at this ortho position, and if it goes here, there is a partial negative charge as ortho and para position. So electrophile choose those two positions for electron donating. Okay. So in case of electron donating group, the ortho and para positions are electron efficient, and for electron withdrawing group, the meta position is electron efficient. So that's why in this case, this Br plus will be entered at this meta position. This as our product. Okay. Okay. This is easy now. So there is a carbonyl group. Is this electron donating or withdrawing? It is a electron withdrawing. So this is AlCl3. This is also a Lewis acid. This is also a Lewis acid. It has a vacant d orbital. So this vacant d orbital, it can take up this chloride and generate this alkyl cation, and this is a electron withdrawing group. This is the electron withdrawing group. So this will prefers this position, and we get our product. At this position. I think these two you can solve by yourself. I am not solving these two. Try. I will give the answer in the next class. Okay? Try. It's simple. You just have to determine which one of this electron donating and withdrawing, then after that is simple. Okay? Let's go to next question. So they have asked that, they have said that from this reaction we get these two types of product. Now from the previous reaction you get an idea that chloride will remove and it will generate this carbocation, and this carbocation will enter to this system. Now how will you get this one? This one is clear. Everyone can get an idea that how this is forming. This carbocation is, and then it will just attack and we will get this one as our product. Now how we are getting this one? Now see, this carbocation is 1 degree. As I was saying, if the product is not, if that the reaction, this was not given, suppose only this part is given, only this, then we will just stop here. But here, if there is a chance of get a higher hybridization carbocation, reaction will go there. So there is this is 1 degree. So there is a chance of hydrogen transfer, and we will get carbocation this one. So this is 2 degree, stable than that of other one. So next, what will happen? So when the benzene ring comes, it will attack, and we will get this one as our product. Okay? Understood? Now if you have a doubt that how this is getting, I draw the elaborate mechanism. This is the hydrogen atom. Okay. Slow step or the RDS, and second one is the fast step. RDS means rate determining step. RDS means rate determining step. Okay. So let's go to the next one. What is rate law? So rate law is the mathematical relationship of a reaction. I think the aromatic substitution is clear. So from this one we are ending the aromatic substitution, the substitution and elimination. We have discussed all type of substitution and elimination. If you have any doubt regarding those, you can ask me. I will try to get back to those questions. So rate law, it is a mathematical relationship between rate with its reactant concentration. So suppose a reaction x plus y, we are getting z. So what will be the rate of the reaction? The rate of the reaction will be dependent upon the reactant, that is x and y, which we have discussed in case of SN1, SN2, whichever the reactant is involving in case of the rate determining step, the rate of the reaction is depending on the concentration of those substrates. Now, this K is called rate constant. This is specific for a specific temperature, and this rate constant changes at temperature. Suppose a reaction, you are performing a reaction. Suppose a reaction is endothermic. Endothermic means if you are giving heat to that reaction gets faster. I discussed in the first or second class maybe that what is endothermic and exothermic. If the reaction is performing after gaining the heat, that is called endothermic. It's taking heat and performing the reaction, that is endothermic. And what is exothermic? When heat is getting generated in a reaction system, that is called exothermic. That reaction is giving some heat. Suppose you are burning a paper, that is a exothermic reaction because you are getting heat from there. That is a exothermic reaction. But if you are melting ice, it taking heat and it getting melt, that is a you are melting sugar, not heat ice, because it's not a reaction. If you are melting a sugar or if you are melting something, that is a endothermic reaction. Or melting a candle, if you are melting a candle, that is a endothermic reaction because it's taking heat and it's getting melt, that is a endothermic reaction. But what is exothermic reaction? If you are burning a paper, that is a exothermic reaction because by this reaction you are getting heat from that, that is a exothermic reaction. So you understood what is endothermic and what is exothermic. Now Suppose endothermic reaction is given. So you are performing a reaction at room temperature and you are performing a reaction at 40 degree or 60 degree temperature. Now everything is same. For this one you have given all the substrate and substrate same for both of them and concentration is same. So X and Y is same. Concentration of X and Y are same. But if the reaction is performing at room temperature and the reaction is performing at high temperature, there will be difference in rate. So which one is controlling? Because X and Y are same. So in case of room temperature reaction, the reaction is slow. But in case of high temperature reaction, the reaction is fast. So the reaction is controlled by the value of K. So from that one we can get an idea that at different temperature the value of K is different. So the rate constant changes with temperature. So if everything is same and you are just changing the heat, the rate constant changes with the temperature. And the rate also dependent on the concentration term of the component. So if suppose you are enhancing the concentration of the X, if it is 1, or if suppose instead of 1 it is 2, so you are enhancing the concentration of X. So if this is enhanced, the rate will be enhanced. So it's dependent on the concentration of the component also. So in case of different type of reaction, here the rate laws are given. So if it is unimolecular reaction, then the rate constant will be like this. So example of this one is SN1. If it is a bimolecular reaction, then that will be this one, because A plus A we are giving the product. If bimolecular can be two types, but the A both are same, and where both this type of reaction happens in case of polymer reaction, when the same type of things are just multiplying. This type of things happen in case of polymer reaction. This bimolecular reaction is example is SN2, where first one is substrate, second one is base. Okay, so you got the idea from that one. Now next is potential energy diagram. So for every reaction we discussed in these three classes, SN1, SN2, E1, E2, E1CV, aromatic substitution. For every one I have shown the energy diagram, energy profile diagram, or the potential energy diagram. So how the energy diagrams are getting drawn, that we will discuss now. So the energy changes that occur during a chemical reaction can be shown in a diagram called potential energy diagram. So the potential energy diagram shows the change in potential energy of the system as reactant are converted into a product. So here are two types of reaction I was saying, endothermic and exothermic. So if this is for endo, and this is for exo. So this is the heat of the reaction. This is the heat of the reaction. So you can see the product is this much amount of heat. Product has this much amount of heat greater than that of the reactant. So product has, this is the reactant energy, and product energy is higher than that of the reactant this much. So product, so get a product with, suppose a person is taller, a person is 6 feet, a person is 5 feet or 5.5 feet. Okay, so to reach that person who is 6 feet, you need a heel of 5 inch. You need a pair of shoes or something which has a heel of 5 inch. So that much of heel you need to get to that person which is at 6 feet. So this is the thing. The product which is already at higher energy, to reactant to get to this product, it needs some heel. But instead of heel in this reaction, it needs some energy to go to that product, because the product energy is already high, it is up than that of the reactant. So this is endothermic. Okay, you can get an idea. I have just tried to make it simpler. Which is the person which is taller than you, to go to that person, you need some heat. So if the product energy is already higher than that of the substrate, so it needs some heat to go to that product, to reach to that product. So where you can get the heat? By giving some why you will get that energy? The product is already has high energy. How you will get that energy? By heat or light or anything, you will get that energy and go to that product. So it's getting that energy. So that is, it is endothermic. It's getting that heat. So it is endothermic. It's gaining that heat and going to that product. And the amount of energy to go to this transition state, this is called, not transition, this is called intermediate. This intermediate state or transition state, or the amount of energy to go to this activation state, or suppose where the phase of the reaction is determined. Activated state, this is called activation energy. This is called activation energy. I suppose in case of exothermic reaction, the product energy is already lower. So someone is which taller, and if we have to talk to a person which is shorter than him, so you have to bend down, right? You have to bend down. So you have to release your energy. You have to release your energy. So that is exothermic. It's releasing energy. It's releasing energy to get to that product. So this amount of energy reactant has to release to get to that product. And this is called activation energy. The amount of energy required to get to that activated state, this is called activation energy. So you understood the difference between heat of the reaction and energy, or enthalpy of the reaction. The amount of energy, different of amount of energy between the substrate and product, that is called heat of the reaction or enthalpy of the reaction. And the amount of energy required to go to the activated state, that is called activation energy. So from this diagram you can get an idea which reaction has less activation energy, exo or endo. Obviously exo. Exo needs less amount of activation energy because it can easily, because it already releasing heat. It itself releasing heat, or it itself releasing energy to go to that product. So you don't need excess of energy to go to that product. So that's why in case of exothermic reactions, that's why exothermic reactions are always more favorable than that of the endothermic reaction. Okay, so that's why exothermic reaction are more favorable. So here they have given an energy profile diagram, and from that one you have to draw an elementary reaction, as I was said. So just try. I don't know you will get an idea or not, but just try. So this is, there will be the substrate, obviously. Here will be the intermediate, and there will be the product. Okay. Now we have to draw this is the activation energy. This is the activation energy. So just try. So what will happen? So this will be our substrate. we go to our intermediate. That will go to the product. Okay. So as this needs less amount of energy and this needs more amount of energy, so obviously this step will be fast and this step will be slow. Okay, understood? I hope it's clear. So next is activation energy. So I was already discussed. What is activation energy? Activation energy is the minimum amount of energy that must be available to the reactant for the chemical reaction to occur. So this is the mathematical term for activation energy. Is called Arrhenius equation. This is called Arrhenius equation. Arrhenius equation. So this is Arrhenius constant. This is the activation energy and this is the rate constant. So this is R is the also constant value and this is temperature. So by this equation you can get an idea that this is the activation energy. The rate of the reaction depends on the activation energy. So from this equation you can get an idea that rate of the reaction depends on activation energy and temperature. Rate of the reaction depends on activation energy and temperature. Now a substance. Now, okay, so you have understood is the simplest. I am not discussing in a elaborate. So if the activation energy, this is called activation energy, and this activation, the rate of the reaction. If the activation energy less, rate will be higher. If the activation energy is more, rate will be slow. If temperature is higher, the rate will be faster, depending on the endothermic or exothermic, that is different case. Now, if you are giving a catalyst, if you know about catalyst, I think you know because in 11-12 the catalyst has been introduced to us. The substance that modifies the transition state to lower activation energy, that is called catalyst. So a catalyst, how a catalyst catalyze the system? So it reduces the activation energy of a reaction. Suppose this reaction is given, this reactant and product. Before the catalyst, the activation energy was this much. But when you are adding the catalyst, the activation energy is this much. So here the catalyst is just reducing the activation energy. And if the activation energy is reduced, what will happen? Whenever the activation energy is less, the rate of the reaction will be faster. Whenever the activation energy is less, the rate of the reaction will be faster. So that's why by using a catalyst you can activate a reaction to react in a faster rate. Okay. So what is the role of the catalyst? By adding a catalyst we can enhance the rate of the reaction. So suppose this is a question that sketch the reaction coordinate versus energy for the given previous problem. So to draw a diagram where according to X there will be energy and this is reaction coordinate. Okay. Now as A is our substrate, A will be here. Now the rate to go to B is 10 to the power 2 or 10 square. The rate to go to C is so the highest rate of the reaction is D. So C to D needs a least amount of activation energy. Suppose we are getting D, so D is the most stable part, one. So D is stable than that of A. And if we draw like this way, so to go A to B, now for to go B to C, you need the rate of the reaction is very slow. The rate of the reaction is very slow. So you need high amount of activation energy. You need very high amount of activation energy. But to C to D is very less. So you need a very less amount of activation energy. So the energy diagram will be like this. Because this is the rate of the reaction. For A, you need a middle type, like this average type of rate of the reaction. But to B to C is very slow, so the activation energy will be very high. And to C to D, the activation energy is very slow, which is because this is the highest rate of the reaction. So this will be our energy diagram. I think you can draw a reaction from it, because we have done both. From this question, we have done reaction from energy diagram, and here we have drawn the energy diagram from the reaction. So you get an idea of the mechanism, that how you can determine the mechanism of the reaction, which step is slower, which step is faster, and to activate the reaction, if you know which step is slower. Suppose a multi-step reaction you are performing in laboratory. Now you have to fasten up your reaction. So if you know which one is your rate determining step, in which step the reaction is getting controlled, and somehow you can activate that step, then you will get a faster reaction. That's why it's very important to know how to draw the energy diagram from reaction and how to draw a reaction from an energy diagram. So let's go to the next question, and this is so now you can easily answer this one. Just try. I'll just give 1 second. Just try to take the option and answer. Pallavi has asked, there is if in a reaction there should be one determining step. If in case of multi-step reaction there will be one determining step. Because if like it has 3 steps, the slowest step will control the reaction, not the slower one. Allah has answered C. So catalyst is a substance actually which increases the speed of the reaction, right? Otherwise, why will add the catalyst? Okay, catalysts are 2 types, like positive catalyst and negative catalyst. If you go into that, so some catalysts decrease the rate of the reaction, those are called negative catalysts, and some catalysts activate the rate of the reaction, which is called positive catalyst. But usually, if we mean catalyst, that will always enhance the rate of the reaction. So here the answer will be, because here you have shown that whenever we are adding a catalyst, is decreasing the activation energy. So if the activation energy gets decreased, so the rate of the reaction will be faster, right? So it will increase the speed of the reaction. It can decrease. If it is a negative catalyst, sometimes in some reaction but in most of the cases, if you are saying catalyst, it means the positive catalyst which activates the reaction by Hammond. Okay. So next is Hammond principle. So in this one, in the next class I will start discussing on this, because we have discussed different type of substitution, elimination. Now today we discussed rate law, how to draw write a rate law, then potential energy diagram, and how this rate law and potential energy diagram coordinate, how a reaction and potential energy diagram coordinate, how you can draw by a potential energy diagram from a reaction, or reaction from a potential energy diagram, or rate law. Everything we have discussed. So from next class we will start different type of principles like Hammond, Hammond principle and all. So I'll just give a recap of that one. So the Hammond principle was put forward by Hammond in 1950, and however the principle was properly recognized by Cartin in 1954, supported by mathematical derivation of Winston Holness in 1955. So what this principle tells to us? The product composition of two conformations which are in rapid equilibrium is not solely dependent on the relative population of the conformer of the substrate, but it is controlled by the difference in the standard free energy of the respective transition state, provided the rate of the reaction are slower than that of the rate of the conformational interconversion. What they say, lots of things they are saying. So if we go one by one, so that is saying that suppose a substrate has two conformers. Suppose conformer means there is two terms. One is conformation and the another is configuration. So what is conformation and what is configuration? Conformation is means that which are interconvertible, like staggered and eclipse. Staggered and eclipse. They are called conformer or conformation. And configuration means Z or E. It can't be converted like those are like specific compound. You can't interconvert them. You can't make a Z compound to E. You can't just rotate like this way and make it E. It is not possible. That will be stable like E in the system. That will not go to E or Z in the system. But a staggered compound can be interconverted to eclipse by just exchanging some amount of energy. Okay, so suppose the two conformers are in rapid interconversion. So now if you are getting two products from each of the conformer, you are getting a product from the staggered, you are getting a product from the eclipse. Now which one we will get, which conformer will react in a faster rate, that depends on the activation energy or free energy of that conformer to that product. It doesn't depend on the concentration of the conformer. What I am saying, if there is staggered and eclipse, and from that one, suppose from staggered you are getting product C, and from eclipse you are getting product D. From staggered you are getting product C, and from eclipse you are getting product D. Now, how can you determine that which one will react faster, staggered or eclipse? That depends on the free energy difference between this staggered and its product and this eclipse and its products. It doesn't depend on the concentration of the staggered or eclipse. It doesn't depend, because if you can imagine that there is staggered and eclipse, and whichever is in higher amount. Suppose if you have in a reaction mixer you have more amount of staggered, then staggered will react faster and you will get the product from staggered, and eclipse will not that much, because you don't have eclipse in the reaction mixer, not much, so it will not give our major product. It's not like that. It's like that if the activation energy between this A and C is less, then this will react faster. and it will give us our product. So it will get diminished and form glass atelier principle. You know, if you remove something from the right hand side, then reaction will go to the right hand side. So it is reacting faster, right? As the activation energy is less or free energy is less, so it's going to the product in a faster rate. That's why it's decreasing. So that's why B will go to A and then A will again react. B will go to A and A will again react. Understood? So it doesn't depend on the concentration of the A. It depends on the activation energy between A and C. Okay. This I will discuss elaborately through energy diagram and example in the next class. If you guys are interested, then you can attend those classes. So this much for today's one. Thank you everyone. I will discuss this in the next class. So this is the recap of today's class, where we discussed about some example of elimination and substitution. Then we discussed about E1CD and its concepts, some examples. Then we discussed about aromatic electrophilic substitution, followed by its reaction coordinate diagram. Then some examples. I gave 2 of the examples to try by yours. If you can just try once, because reaction mechanisms, until you solve it by yourself, is not possible to solve unknown problems, because in some examination or any national level examination, you will not given the same question from the book. They will give question from anywhere. So you have to attempt those questions by your understanding. So until you are not solving those questions by yourself, you will not get that understanding if you are giving an unknown problem. So try to solve it by yourself. Then we discussed about rate law, potential energy diagram. We solved some problems also, activation energy. And then we are giving a recap of Hammond principle, which we discussed in the next class. So thank you everyone. Have a nice day.